Okay, so remember in this topic of quantum physics, we are talking about the idea of EM radiation as particles called photons. So the second phenomena that we can only explain if we take EM radiation to be packets of energy called photons is this phenomena called line spectra. So whenever you have a gas discharge tube, which is basically a container with a tube filled with low pressure gas, okay, this one we have that apparatus in the lab, so I will show you guys. And if you apply a large voltage across this gas, the gas will glow. Okay, you'll see a specific color, but the color that you see is like a mixture of a few colors but you will see as one combined color. So what happens is, if you're using, let's say, hydrogen, and you take the light and you pass it through a diffraction grating, you will see the components of the colors within this color. So you notice there'll be 4 colors. So for hydrogen, there are specifically 1, 2, 3, and one more not so clear, 4 colors. For helium, there are more, then argon even more, mercury even more. So what happens is, because all these colors that you see are in the form of lines, so it's a spectrum of colors in the form of lines, so we call it line spectra. That means spectrum of colors in the form of lines. So what actually happens within the gas here that causes the gas to glow and produce specific colors? So who managed to explain? Actually, it was Niels Bohr. Now there was another theory that disagreed with the model of an atom, because the model of an atom says you have a nucleus which is positive and electrons which are negative orbits the nucleus. But Maxwell's theory says whenever a charge accelerates or decelerates, it will emit EM radiation. So when the electrons are orbiting around the nucleus, it is undergoing circular motion. So it has what kind of acceleration? Centripetal acceleration. So by right, if you follow Maxwell's theory of EM radiation, so if we undergo centripetal acceleration towards the center, by right it should also emit EM radiation. So what will happen to the electrons is the electrons will lose energy, which is Ke, and then it will spiral towards the nucleus and finally collapse and disappear. But does that happen or not? No. So therefore, Niels Bohr managed to solve this problem that he couldn't explain, the contradiction between Maxwell's theory and the model of an atom. And at the same time, he also managed to explain this phenomena called line spectra. Now, according to Niels Bohr, right, there are specific orbits that the electrons can orbit around the nucleus without having to obey Maxwell's theory of EM radiation. So he's not saying that Maxwell is wrong, because Maxwell's theory was proven to be right. For example, in the case of deceleration of electrons when they hit an anode, that causes X-rays to be emitted. That means to decelerate the electrons, you produce X-rays, which are EM radiation. So his theory is definitely correct. And in fact, the how you generate radio waves is also by accelerating and decelerating the electrons through an aerial, and you also get radio waves. So Maxwell's theory is definitely correct. All right, but the model of an atom seems correct. So what did Niels Bohr say? Very conveniently, he said Maxwell's theory is correct except for specific cases. So what are the specific cases? Now, according to Niels Bohr, there are certain orbits, we call it the allowed orbits, where the electrons can go around the nucleus without having to obey Maxwell's theory. So these are exceptions. For example, you know in chemistry you learn about the shells, the N shell, P shell, what L, L shell also got, right? SP, got L or not? No. When did I learn L from? Okay, so I didn't fail, okay, anyway, don't talk about it. Okay, S shell, P shell, whatever shell. So these are what you call as allowed orbits. So allowed orbits means the electrons can go around the nucleus and will not emit EM radiation. So Niels Bohr suggested that the electrons will naturally be at the lowest energy state, which is the lowest orbit, which is a lower shell. Remember your chemistry also you learn you must occupy the lower shell first before occupy the higher shell. So same concept lah. So the electrons will occupy the lowest orbit, which is the lowest energy level. We call it n equals to 1. right? Now, when it wants to move from one orbit to another orbit, what happens? Now, Niels Bohr says each orbit corresponds to a specific energy level. You know why? When the electrons are orbiting around the nucleus, what energies do the electrons have? Kinetic energy and potential energy. So each orbit, the electron has a specific KEPE, which is given by the energy level. For example, the lowest orbit, just give an example, let's say it's negative 15 electron volt. Now the higher orbit, it means it has more energy, so this orbit corresponds to a higher energy level, let's say negative 10 electron volts. So another higher orbit, another higher energy level. So this goes on and on until you reach infinity, where your energy level maximum is 0. Because remember, for the case of attractive forces, the maximum PE is 0. So that means when you go to infinity, your PE is 0, right? So that means the total energy also 0 lah. So which means to say, for an electron to jump from from a lower orbit to a higher orbit, it is possible, provided it absorbs an exact amount of energy. It must be exact. So how will the electron absorb an energy to jump to a higher orbit? Very easy. Three different ways. Either it collides with an electron, it collides with an ion, or it absorbs a photon. Now, provided the energy it receives matches the difference in energy levels, then it will jump. Example, if it absorbs the difference between these two, which is how much? This energy level and this energy level. 5 electron volts, right? Then it will jump from here to here. If it absorbs, let's say between, it jumps from negative 15 to negative 7, how much must it absorb? 8 electron volts, then it will jump. Then some people ask me, what if it receives like halfway or not enough, let's say 4 electron volts. 4 electron volts can jump or not? So it will not jump. It will not even move up. Which explains why, that means, for example, if you give it photons, if you give it photons that carry energy of 4 electron volts, the electrons will refuse to accept it. Which explains why, you know your photo cell, the one that we use solar cells to generate electricity. So far, the maximum efficiency is only about 40%. You cannot achieve higher than that because whatever material you use, for the electrons to jump to high energy level, you must absorb photons of specific energy that matches the energy level transition. So you can never have all the EM radiation that matches all the energy level transitions. So most of them will just be ignored. Therefore, your efficiency is only up to 40%. So far, I heard now can go above 40%, the latest. So that is just how efficient it is. Because if the energy doesn't match, it doesn't jump. That's end of story. If it matches, it jumps. So let's say it absorbs 8 electron volts from here and jumps from here to here. So that means it will jump from this orbit to the third orbit. But once it jumps to the higher orbit, remember there's an inner shell vacancy, which you learn in chemistry must be refilled immediately, right? So in physics, we say that when it jumps to a higher energy level, it is very unstable. So it has to quickly return back to the ground state. So it has no time to like jump here and then absorb and jump some more and absorb and jump. No time. The moment it jumps here, it is so unstable, it falls back straight away. So it cannot take multiple steps up. But once it falls down, it can take multiple steps down. It can straight away fall down, or it can take multiple steps and fall down. Now, each step that it falls, or each transition we call it, will cause the electron to lose a specific amount of energy, right? For example, if it falls from here to here, it must lose 3 electron volts. If it falls from here to here, it will lose another 5 electron volts. Or it falls straight away, it will straight away lose 8 electron volts. Now, this energy that is released in the form of a photon. So what comes out is, let's say from here to here, it falls, it will generate a photon. If it falls from here to here, another photon. It falls from here to here, another photon. So every time it falls, it generates a photon. And since the energy of the photon is given by what energy? What formula? E equals to hf or hc over lambda, right? So every time you lose your energy in the form of photon, you produce a specific frequency or wavelength. which is a specific color, which is a specific color. So which means to say, since the energy levels are all very specific, right? Like specific values here, every time it falls, it will definitely produce photons of specific wavelengths or specific frequency. So this explains why each gas produces specific colors, because the energy levels for each gas are specific one. For example, hydrogen only has one proton and one electron. So the PE that the electron has definitely different than the electron in, let's say, helium. Because helium will have how many? 2 protons and 2 electrons. So the PE of the electron in helium is definitely different than the PE of the electron in hydrogen. So they all have specific energy levels. So when they fall, they also produce specific colors. So do you realize that you can only explain this phenomena of line spectra if you treat this EM radiation as photons, because it comes out as a energy, but it's a packet we call a photon. Do you understand that? Okay? So therefore, the formula that you will use in line spectra will only be this. Okay? This one. Delta E equals to, now what is delta E? The difference in energy level. The difference in energy level, which is, let's say, E2 minus E1 here, will give you the energy of the photon that is released, which is HF or HCO lambda. Understand? Does this formula look familiar? This is the one that you learned from Max Planck's theory, right? From Max Planck equation of a photon, so it's the same thing. Alright, Planck constant, h, c is speed of EM radiation vacuum. Alright, so you can either write as HF, you want frequency, or HCO lambda if you want to find in terms of wavelength. Now, the spectra that you have to be very familiar with will only be the hydrogen spectrum. Now, why they only ask you to memorize the hydrogen spectrum? Because do you realize it's the simplest one? We only got how many protons and how many electrons? 1 proton, 1 electron. Therefore, it is the simplest form. So, what happened was, there were different scientists that examined the EM radiation emitted from the hydrogen gas. So you have 3 different scientists. The first scientist, which is Balmer, found out there are 4 specific colors of visible light, alright, which corresponds to these frequencies. That one you have to memorize. And then later on, other scientists, like Lyman and Paschen, they discovered the other EM radiation, so which will be infrared and also ultraviolet. So we look at it in the next slide. Okay, so if you look at this diagram here, you will notice that the visible light is called the Balmer series, and then you also have ultraviolet called the Lyman series, and the infrared called the Paschen series. Now what you have to realize, or what you have to remember in your exam, is the sequence. Now you notice that if the electron falls all the way to the ground state, it will always produce ultraviolet. So where it falls from is not important. It can fall from n equals to 2, n equals to 3, 4, doesn't matter. When it lands here, it always produces ultraviolet. But if it lands one level higher, which is n equals to 2, it doesn't matter where it comes from, it will always produce the visible light. You understand that? Okay, so you always produce the visible light, which is the Balmer series. And if it comes from any level above, but it falls to n equals to 3, it will always produce infrared. Okay, so you must remember the sequence. Infrared, visible light, ultraviolet. Actually, it's quite logical. Between these 3, which is the most energetic? Ultraviolet. So it must fall to the lowest level. Then the less energetic will be visible light, so it falls one level higher. Then the least energetic infrared, so it's the highest level. So the smallest energy level transition. Now, of course, it doesn't end here. All the electrons will fall to here. It must continue. I'm not saying it will end here. It will continue here, or it goes back straight. Doesn't matter. But this transition at first will produce infrared. After that, it's a different story. But it must go back to the ground state. Okay? Remember? Right. So this is another illustration. So if it falls from n equals to the n higher level to n equals to 1 Lyman, from higher level to n equals to 2 then you will get the Balmer series. And if the electrons fall from a higher level to n equals to 3, then you will get the Paston series, but it is not shown in this diagram.